Well, welcome back, everybody, to this joint webinar from Teleps and Specialized Imaging. So, well, first of all, good morning or good afternoon to you all. My name is Jean-Philippe Gagnon, and I'm a field application engineer at Teleps, and I'll act as chairman for this presentation today. So presentation will last about 45 minutes. So the general outline is as follows. I will give a general introduction as well as present Teleps and its product lines. And then this will be followed by a presentation by Jolyon Cleaves of Specialized Imaging about how their line of tracker systems can track supersonic objects and provide high-speed video and measurement. Then Stéphane Boubanga will present on tracking flying targets and measurements of their surface temperature using high-speed infrared imaging. If you have any questions during the webinar, don't hesitate to ask them via the question box in the GoToWebinar app. There will be a 10 minutes questions and answer period at the end of both presentations. Note that we probably won't have time to address every questions during the Q&A session. However, every questions will be answered offline by our panelists, and the Q&A document will be distributed to all participants along with a link to this to the recording of this presentation. So let me first start by introducing Teleps. So Teleps is located in Quebec City in Canada. It was founded in 2000 and has grown significantly since then to over 90 employees. Teleps designs and manufactures high-performance, hyperspectral imaging systems and infrared cameras for defense, industrial, and academic research applications. Teleps also offers R&D services for optical systems technology development in order to respond to the specific needs of its customers. While being headquartered in Canada, Teleps caters to an international market using offices in the US and France and an efficient global network of distribution and representation. Teleps manufactures 4 different types of cameras, each category featuring different models. The HyperCam is our flagship product. It features high speed, but also very high spectral resolution that translates into thousands of spectral channels. The multispectral infrared cameras are equipped with an 8-position fast rotating filter wheel, which allows the scene signal to be split into different spectral bands rather than just one broadband image, thus enabling spectral signature analysis. We also have high-speed infrared cameras like the M3K that is featured in Stéphane Bouganga's talk later on. That was the camera used to collect infrared images. So this camera, this camera offers an impressive temporal resolution. So it works at full frame up to 3,000 frames per second. And in sub-window mode, smaller windows, it can work at 100,000 frames per second. And finally, we have our dynamic range cameras that can measure highly contrasted scenes up to 2,500 degrees Celsius. I want also to mention briefly our new line of long-range zoom cameras that combine the characteristics of our fast IR infrared cameras with impressive ranging optic capabilities. So these cameras these cameras have an integrated motorized continuous zoom lens with autofocus ranging from 30 to 6 160 millimeter focal length with an horizontal FAW varying from 18 degrees to 0.83 degrees. So they are extremely sensitive and thus enable the detection of challenging targets. So now I'd like to introduce to you our first speaker, Jolyon Cleaves, Sales and Marketing Director at Specialized Imaging Limited. Jolyon's background is a degree in aerospace engineering, but moved into sales starting at DRS Headland, where he first learned about ultra-high-speed imaging systems, framing, and streak cameras. Jolyon moved on to selling phantom high-speed cameras, initially for Photosonics International in 2000, and then directly for Vision Research from 2007. He joined Specialized Imaging in 2018. But Jolyon will talk about how their line of tracker systems can track supersonic objects and provide high-speed video and measurement. So Jolyon, if you're ready, take it away.
Thank you very much. Can you guys hear me okay?
Yeah, I can hear it just fine.
Very good, excellent. Okay, and can you also see my screen there?
Yeah, looks good from my end.
Great stuff. Okay, well, thank you, Jean-Philippe, for that introduction and for everybody else who's joining us today. Before I go diving into the tracker systems and some of the considerations that perhaps need to be thought about prior to using them, I'll give you a slight background on Specialized Imaging for those of you who haven't perhaps heard of us before, because even though we are an international company with offices in America, UK, Germany and China, there are some people that perhaps haven't heard of us before. As our name suggests, we are focused on pretty much a niche market of ultra high-speed imaging and their applications. We were a relatively young company, founded in 2003 by a group, or at least a pair of highly experienced engineers from a company called Headland Photonics, which later became DRS Headland when I was there for a short spell. And Headland Photonics itself was really synonymous with ultra high-speed imaging since the 1960s, developing and designing those systems over that period of time. Some of you have been in research institutions for some time, may be familiar with the Imacon 790 cameras, which was a purely analog system up to about 50 million frames per second. And in the 1990s, the guys that started Specialized Imaging later on were instrumental in digitizing that technology and bringing out the Imacon 468 and then latterly the Imacon 200. And they were capable of up to about 200 million frames per second. In the intervening years, Specialized Imaging has broadened its capability. So we've introduced the SIM range of cameras for some years, which is capable up to 1 billion frames per second with up to 32 images. We've broadened our ability to, in the high-speed imaging market, where we've developed our own sensor and camera, which is now the Karana ultra high-speed video, a really true ultra high-speed video camera capable of 7 million frames per second at full resolution. And then finally, the reason we're here today, or part of the reason here, is to look at the Tracker 2 systems. So generally speaking, we've broadened our capability to develop and manufacture new imaging systems and some of the necessary peripheral devices, not just the tracker systems, but also the triggering and illumination systems. Now, the two trackers that we have developed so far really use the common core technology, and that's a motor which is moving a mirror in order to track the predicted flight path of any particular projectile. So we're not actually actively feeding back into the system, we're simply following the predicted flight path. The core technology of these two is the same, but rather than me trying to describe it, I've got a small animation which hopefully should play without sticking too much, and hopefully the music won't be too loud. It's only about a minute or so, but I'll let this play now. Okay, so I hope that sort of described at least what the Tracker 2 capabilities are. As I say, the core technology of the two systems is pretty much the same. The bigger difference with the Tracker 2 is it's fully motorized in azimuth, elevation and roll of the camera and mirror container, whereas the Tracker Lite is a purely manual system and strictly speaking only designed for horizontal firings only. The scan ratio is a little bit different for both of them, but I'll go through that in a later slide. The positional and scanning accuracy of the two is the same. And although I said earlier we don't actually actively feedback information to these systems, there are some point feedbacks that we can put in at various points along the flight path. Perhaps the bigger difference of these two systems is that the Tracker 2 can pretty much hold any high-speed video camera with up to 800mm focal length lenses, which if you're looking at particularly big projectiles is what you really need, whereas a Tracker Lite is designed around the Phantom or Photron mini type cameras with up to 200mm or maybe 400mm focal length lenses. So getting down to the sort of the nitty-gritty of how do we use this tracker system, because it's not a simple case yet of just sticking it in a field, pointing it in the right direction and off you go. You do have to survey in the relative locations of the tracker and the gun or the launcher system. What I've got here is a typical plan view of a horizontal firing where the mirror is arcing through 90 degrees plus or minus either side, 45 degrees either side of a midpoint. We can actually go slightly more than 45 degrees, but for the sake of easy calculations, I'll stick to 45 degrees. So whatever your standoff distance X is, your scan distance is going to be double that. Your start point is typically 1 to 5 meters in front of the launcher or the gun muzzle. This is to allow the tracker to accelerate the mirror up to the speed that is necessary. And also, if you're looking at small arms, then that distance is usually 1 meter. If you're looking at 155 artillery pieces, because of the big muzzle flash, that's typically between 5 and 10 meters in front of the gun. The tracker system and the camera is controlled 100 meters from the tracker system, usually using 100 meters Ethernet cable, so the safe distance behind the gun or the launcher system. Now, I mentioned earlier about the scan ratio, and this is a simple calculation of the maximum projectile velocity divided by the standoff distance x. And if you recall on the previous slide, I think for the Tracker 2 it was 100, so theoretically if you had a standoff distance of 50 meters, then the maximum projectile velocity would be around 5 kilometers per second. In theory that's not always the case, because you have to allow some acceleration of the mirror, so typically it's about 80 to 80% of this. Once you've surveyed in the tracker and the gun, you have to also input to the tracker system an assumed velocity, because we can't measure the velocity necessarily right at the muzzle itself. So it gives the mirror time to accelerate up to speed. Now, on some ranges, you might not have that kind of standoff distance available if there's trees, wire fences, buildings, and other obstructions in the way. So we can skew the position of the tracker system to either be a little bit more towards the gun muzzle or to a little bit towards the target. So you can still maintain that scan distance, but you have a slight perspective difference, which may be useful. If you're looking at missiles, and if it's a wire-guided missile, for example, then you may want to look at the wire guiding, the wire coming out of the back of the missile. Or if you want to look at the tip of the projectile to see what the heating is, as Stéphane is going to describe later, then perhaps you want a slightly more frontal perspective. So really, in order to prepare the ground for the use of such a systems, you do need to survey in where the tracker and the launcher is relative to each other. Obviously, you need to know the direction of the intended projectile flight, so you can accurately measure that standoff distance, which is quite an important distance. And typically, we can get down to 5 to 10 centimeters accuracy on that, and also the distance between the trigger and the start point. You need to input the projectile muzzle velocity as well to give the mirror a fighting chance of catching up with it in good time. If you have a drag coefficient related to the projectile, that can be inputted into the tracker system. And also if you have an accelerating projectile and you know the velocity profile, that can also be added in as well. So it's not just a one-trick pony. We can look at other projectiles as well. Now, going back to the horizontal firing view from before, for a standard horizontal firing with a gun elevation of 0 degrees and a 50-meter standoff, your scan distance is 100 degrees, as we've established. But the azimuth, elevation, and roll of the camera mirror pod is pretty much all 0. An interesting point here, which I'll touch on later, is that even though your closest distance is 50 meters, your furthest distance is just under 71 meters, which can present some difficulties, which I'll touch on again a bit later. Now, what happens if you want to incline the gun? Whether that's just a few degrees because the projectile isn't hitting the target and you need to raise the gun elevation, or you want to do inclined indirect fire of an artillery piece. All these distances you have to measure are now suddenly up in the air, which are much harder to measure. But luckily, what we do in order to set the system up is we assume you do horizontal firing first and measure out the plan and the positioning of the tracker relative to the launcher. And the only additional measurements you have to do for an elevated firing is the gun elevation, the distance between the pivot point of the gun or the launcher to the start point along the ground, and the barrel length from the muzzle to the pivot point. So the plan view will go from this to this with a slight skew. And the standoff distance goes from 50 to 63 meters if you have a 45-degree elevation, and your scan distance then goes from 100 meters to 141 meters. So things do change, but perhaps the most important thing is the azimuth elevation and roll becomes a really non-trivial solution because your tracker and gun and start point are all fixed relative to the gun, relative to where the projectile is going to be flying now. And your furthest distance away is now 93 meters. So if you're doing an inclined firing together with all the other survey information that you input into the software, you need to know the trunnion to start position, trunnion to muzzle, and also the gun elevation. Luckily for everybody, the tracker 2 software, control software, can calculate the correct angles and position itself automatically. So there are other considerations, not just the tracker and the survey and everything else, but what kind of camera are you going to put into this system? Whether it's a thermal camera or a high-speed video camera. Typically, frame rates are between 2,000 and 10,000 frames per second, depending on the speed of the projectile. Because we're following the projectile rather than it passing the field of view, we can have slightly longer exposure times. So typically between 200 microseconds and 50 microseconds. What perhaps needs to be thought about a little bit is if you want to, on the day of the test, speed up the frame rate, that's going to reduce your field of view. And here's an interesting point where if you have a focal length of lens, because your distance from the tracker to the projectile is varying throughout the flight, so from the two ends of the track it's going to be further away than at the midpoint, then that field of view is going to be changing. So again, you perhaps have to consider your camera pixel resolution and the camera pixel size if you need to think about what kind of frame rates you need in order to get enough temporal resolution. And the final point here is really an often overlooked aspect of using a tracker system, and that's partly down to this changing distance from the projectile to the tracker, where because of the changing distance, you have to change the f-stop to increase the depth of focus, and typically you're going to have to reduce that down to a number where you increase the depth of focus enough to keep the whole track in focus. That then brings into play perhaps the camera sensitivity, what pixel size camera you use, and also the ambient lighting conditions. I'll give you some examples here of a field of view change. If you had a sensor that was 1024 pixels wide with a 50-meter standoff and it's 10 micron pixels, these are the kinds of fields of view that you would have at the beginning and the midpoint and the end point for these focal length of lenses. So if you're looking at a long rod projectile, it's about a meter and a half long, you might be looking at a 200 to 300 millimeter focal length lens. If you're in order to get a more sensitive camera, then you have a 20 micron pixel, then these fields of view are going to double. So you would potentially have to double your focal length of lens as well. What we tend to use as a matter of, at least for demonstration purposes, to make our lives a bit easier, we use zoom lenses. So from 120 mil to 300 or 300 to 800 millimeter. And sometimes we use doublers or teleconverters to extend that even further still. And to touch on the depth of focus that you require during a track. If your standoff is again 50 meters, your required depth of field is quite a large 21 or just under 21 meters. So for a 600 millimeter lens, and these values here are really for a theoretical lens, so for a real lens it might be a little bit better. For 2.8 you're only going to get a 1.3 meter depth of focus. For f11, 4 meters, and for f32, 11 meters. Now f32 is really shutting the lens right down, so you need an awful lot of sunlight in order to see anything. It would be quite dark otherwise, but you do happen to have just under 12 meters of depth of field. If you focus the lens at the 30-degree point, and when I say 30 degree, that's 30 degrees in the arc of the mirror, then these are the kind of focus limits that you've got. And how do I know this? Well, the software that you get with the tracker allows you to, or includes a lens calculator, so you can put in camera parameters, lens parameters, and tracker parameters, and from that you know what your field of view is going to be, depending on the pixel size and focal length of lens and resolution, and also what your lens focus is going to be in relation to the various distances. So those are the general considerations if you're thinking of using a tracker system where you need to survey things in, you need your predicted muzzle velocity, and some of the considerations for the high-speed camera and the lensing and the f-stop that you'll need for sufficient depth of focus. Now, two other considerations perhaps that need to be thought of for this particular type of presentation. One is that with IR cameras, you probably are going to have to remove the glass of the tracker system because most of them won't transmit IR frequency light. And also sometimes projectiles don't always do what they're supposed to do, and they can do some rather strange things. Now, hopefully this video, some of you might see this in rather jerky fashion, but when you download it or view it after here, this should be quite nice and smooth. The top projectile is pretty much behaving as advertised, but the bottom one is clearly not. It's breaking up, changing its drag coefficient, and probably has a different muzzle velocity as well. So how did we manage to keep both those projectiles in the field of view throughout the track? What we do is we place detectors under the field of view which can detect the passing of the projectile over the top. So if you want a position change, so perhaps the trigger was a little bit early or a little bit late, you can use a single trigger. If your velocity, predicted velocity, is incorrect or inaccurate, then you'll need two trigger systems with a known distance between them. And all this can be surveyed in and put into the tracker itself. And of course, if it really is unpredictable, you can put up to 5 or 6 further down range in order to make sure that the projectile is going to be in the field of view. And this is a typical sky screen type of projector. This is the one we make, but there are other ones out there as well. And by way of example, here's a 3D tracker system that we had, one tracker either side of the flight path, looking at the similar Huygens probe that Stéphane is going to be talking about with his thermal cameras. And in early stages, you can see that the projectile itself was almost outside the field of view. And with two detectors, we managed to put it right back into the middle of the field of view. So the system does work quite well. Okay, thank you very much indeed for listening. I look forward to your questions a little bit later. I will hand you back to Jean-Philippe and then to Stéphane.
Yeah, thank you very much, Jolyon. Very interesting talk. So now I'd like to present to you our second speaker, Stéphane Boubanga, who is a field application engineer at Telops. So Stéphane received his PhD degree in condensed matter physics in 2008 from Montpellier II University in France. He worked as a researcher at Los Alamos National Labs in New Mexico, US, and associate professor at Tohoku University in Sendai in Japan. Since August 2017, he's been working as a field application scientist at Telops in the Paris office. His research interests include infrared thermography, as well as infrared and terahertz remote sensing. So Stéphane will talk about the high-performance temperature measurement deployed on a specialized imaging projectile tracking mechanism. Telops cameras perform at thousands of frames per second and with the highest sensitivity. So with these technologies combined, it's possible to perform unprecedented thermographic measurements, even at supersonic projectile speeds. So Stéphane, if you're ready, take it away.
Yeah, thank you, Jean-Philippe, for the presentation. And thank you, all of you, for attending this webinar. Let me see. And I don't know if you hear me and if you see my screen.
Yeah, both of them. see your screen and we can hear you well.
Perfect. Yeah, in this part of the webinar, I wanted to show you that as you saw on Jolyon presentation with visible cameras, Telop's high-speed infrared cameras can also be used with those trajectory trackers. The infrared camera will give you all the same input you could obtain with high-speed infrared cameras, but additionally with an high-speed infrared camera, you will have the possibility to directly measure the surface temperature of the flying target. That surface temperature distribution could be of a high interest for instance, for the design of projectile materials or on the shape of the projectiles, but also can be kind of necessary inputs to access the performances of guns, bombs, or thermal reentry protection systems used by planetary reentry Earth vehicle. So this work was done in collaboration between Telops, as you understood, for the infrared cameras, Specialized Imaging for trajectory trackers, and Institute of Saint-Louis, which is a German-French research for the ballistic test range, actually. Now for the trajectory trackers, Jolyon already described those. We used the trajectory tracker 2 with low inertia silicon mirror, and the mirror was moving at a speed of 1 kilohertz with our infrared cameras in there, controlled via a 1 gigabyte internet in here. And the Telops camera used for this ballistic test was M3K with 200 millimeter length. As Jean-Philippe Gagnon described at the end of the beginning of this talk, he described what makes those high-end infrared cameras so unique. One of the unique performance of this M3K camera is that it can reach up to 3 kilohertz full frame, and reducing the size of the ring window, we can reach up to 10 kilohertz, which is well above the 1 kilohertz of the trajectory mirror movement here. The projectile used for the ballistic test was reentry space probe model made by ISL, as you can see here. And the dimension of the probe was 80 millimeter in diameter, 50 millimeter in height, and the probe was designed to reach up to 2 Mach numbers here. We painted the probe with high emissivity paint to minimize the reflection from the surrounding object and to ensure that we only measure the heat distribution generated by the hydrodynamic effect on the probe here. Actually, you can use 3 types of Telops cameras. Here, this is the M3K. I described it with a FPA of 320 by 256 pixels with a pixel size of 30 micron. But you can also use the camera model we call M1K, which is full from 64 by 512 pixels of focal plane array to 25 micrometer, and full frame can reach up to 1 kilohertz. Here, those two are mid-wave cameras, but you can also use one of our long-wave cameras, which is V1K. From 7.5 micron to 11.5 micron, 640 by 500 by 512 pixels also, and 25 micron pixels. Also, full frame is 1 kilohertz. You remember that the mirror trajectory tracker mirror was speed was 1 kilohertz. So you can also use those two cameras there. Now, this is pictures of the test side. I told you that this is a ISL open aeroballistic testing range located 25 kilometers north from Saint Louis here in France. This is an open range certified for flight firing over a maximum distance of 1 kilometer, which is quite sufficient for ballistic research. You can see panoramic view of the test side here, and here typical launcher, and the target trajectory was is here. We used for this ballistic test two trajectory trackers, one on this side with a visible high-speed camera, and another one on the other side with high-speed infrared cameras. And the data recorded with those two trajectory trackers are compared in here. The trajectory tracker with the visible camera was set, and were able to measure the whole trajectory of the probe, but the trajectory tracker with the infrared, high-speed infrared camera only measure a part of that trajectory. This was just a matter of space allocation and configuration. So you will see in the video I will play. So, but the trajectory tracker with IR could also measure the whole trajectory if the space was allocated. Now this is the visible video. You can see that video there. I can play it until the end. There you will see the tracking. There I will get back to commenting the data collected there and the launching. Again in here, and if I go back, you can see from the beginning the firing in here, and then later on you can see here the separation between the probe and the surrounding. The probe is here, and the surrounding petals and the pusher plate used to protect the probe and prevent hot gas from reaching the probe, because we were measuring that heat distribution on the probe. We didn't want to have that additional heat in here. And then during the flight, you can see shock wave developing here on this visible video here. Now, if we go to the IR video, if I play that IR video, you will see the probe appearing here. This later on it's appear, and then it's adjust, and then you do see the tracking, and you can see shock waves here within this higher video, and can see shock wave there, and you can see shock waves here and in here. So with this higher camera, you able to track and to see and get almost the same informations you were having with the visible camera. You could see shock waves in there, and you could see also heat distribution in the front of the probe here compared to the back of the probe. The heat is the temperature is higher here compared to the back, and this temperature increase on the front of the probe is attributed to the aerodynamic effects in here. And concerning the shock waves, also I wanted to stress that in this configuration with test range and firing, this is the first observation of those shock waves with an infrared camera. And the additional advantage of an infrared camera is that the infrared cameras are not affected by the weather conditions. So at night or under low level light level, one can still collect sensitive and quality data with infrared cameras. This is a picture obtained from this IR video, where you can see the shock wave in here the front of the probe and the back of the probe, and this is the temperature distribution here in blue on the back of the probe, in red here on the front of the probe versus the tracking time in here. We saw temperature difference of up to 7 degrees between the front and the back of the probe here, and also we observe, as you can see in this blue curve here, nearly constant or a slow monotonic decrease of temperature on the back there, but when you see in the front, the dynamic is completely different. You can see temperature increase here, cooling, temperature increase there, cooling, and temperature increase in here. And the only physical phenomena that can explain such difference of dynamic between the back and the front of the probe is the probe interaction with shock waves, and also the heat exchange between that wave and the probe. We also notice here that we have those increase in here, or those increase correspond to the appearance of a shock wave in the infrared image. We also did CFD simulations based on the Navier-Stokes equations, and so showing the temperature increase in the front of the probe, as you can see here, and then you need to solve the heat conduction equation to evaluate how this heat is transferred into the surface of the probe material actually. We also did test, firing test at low speed or low Mach number, and this compare the result we obtained at 1.3 Mach number versus the one we obtained at 1.9. I already showed you the result we obtained at 1.9. If I play the video obtained at 1.3 Mach number, here you will see the probe appearing here, and then the tracking. You can see the probe there, and on the front of the probe you can also see that the temperature is higher here, similar as you could see with the test at 1.9. You can even see shock waves in here in this video, but the shock waves at 1.3 are lower. So this graph, these curves here compare the temperature obtained at 1.9 and 1.3 temperature on the front of the probe. Actually, you can see that the temperature increase in the front of the probe at 1.3 is lower than 1.9, and this kind of justify that that temperature increase is really induced by the aerodynamics, because it's only speed dependent here. Then you can also do some fitting here and extract the heat exchange characteristics times of the overall cooling here we obtain, and also with the interactions with the shock waves here, and get deeper insight into the science there available for scientists studying those heat exchange problematics, but also available for engineers, for example, working on a material fabrication process. Now, the dynamic parameters and the trajectory measurements can also be done here with the infrared data or infrared video, just as you would do it with a visual video here, solving dynamic flow algorithms here, for instance, Cadane-Lucas Tomasi algorithms, plus Kalman filtering and Hungarian algorithm. Here you can extract the space probe velocity maps, here acceleration maps, and the other trajectory dynamic parameters that can allow you to analyze the target trajectory here. And on this last slide here, I wanted to show you results. One example result of that output dynamic flow analysis frame by frame, where you can see the velocity map. The velocity are shown there as red arrow vectors on that graph there. Then I come to the conclusion. I hope I convinced you that our high sensitive infrared cameras are good, can be used for the ballistic tracking. Here we were able to successfully see shock waves and track that Rion-T probe there and analyze the temperature at the surface of that probe there, and extract. We can also extract the dynamic, trajectory dynamic parameters in there. I will leave you with this slide and give back the mic to Jean-Philippe for the questions. Thank you for your attention.
Thank you very much, Stéphane. So I'd like first to thank both of our speakers today, Stéphane and Jolyon, for their excellent work, nice presentations. As I said at the beginning, we'll have we still have a few minutes for questions, Q&A session. So I'll take back the display. We have a few questions here from participants, and as I said at the beginning, don't hesitate to ask questions. So even if we don't have time to go over all of them today during this Q&A sessions, all the questions have been logged in and will be sent to our panelists, and they will answer them offline, and our Q&A document will be sent to all the participants along with a link to the recording of this presentation. So let's dive right in. A few questions from David Reinecke. I'm not sure if I'm pronouncing correctly. I hope I do. About the tracking system for so questions for Jolyon. First of all, first one, how would you set up a tracker for an air-launched weapon and not an artillery gun?
Yeah, the system really is designed for ground-based gun systems or ground-based rocket launches on the basis that it's got to be a slightly more predictable flight path. As I say, we don't really offer a lot of feedback from the projectile itself. So really, I don't wish this to be a sales pitch, but what you really need is something like a LOMA system. If you go to our website, we've got an optical tracking system, which you would typically use, whether that's a photosonic CTM or the LOMA system. So that's what you would typically use. This is really more for guns and missile launches that are ground-based first.
All right, thank you. Follow-up question from David as well. Can a system be used to track rockets, bombs flying in if one has radar tracking of the rocket slash bomb? Yeah,
we can't actively put in the elevation and azimuth from a tracking radar system. The LOMA system can do that, but the tracker system can't do that. It's not as sophisticated, if you like, as that. We have had people want to look at rockets coming in, hitting a target. So it's sort of almost the reverse of an artillery gun in that you've got missiles or bombs or whatever is coming in. But again, it's got to be a known or easily repeatable and predictable flight path. You can't always do it quite so easily where the mirror is only tracking along one axis. So in theory, you could do, but we haven't done that yet. And this is just for something coming in, hitting a known target.
All right, very good. And then probably have time for a few more. Question from Swati Sinha. What is the resolution capability of the system?
When you say resolution, I'm not quite sure. I guess you mean perhaps camera resolution, and that's really down to whatever camera you put in there and whatever frame rate and resolution that you're looking for. And that's what I suspect that you mean by that. So really and truly, it's down to what camera you want to put in there. High resolution, high-speed video cameras tend to be small pixel sizes, which means they're going to be quite insensitive. So there are limitations to the type of resolution you're going to be capable of using based on the sensitivity of that particular camera. As you saw in the presentation, you do have to stop down the lens in order to increase your depth of focus to keep the whole track in focus. So if that's not what you meant, then send us perhaps a slightly more detailed question, and I'll answer it offline.
Yeah, exactly. Yeah, you can also always post questions afterwards. For maybe in addition, and last one, is lens calibration simple for the tracker system from David again?
Yeah, lens calibration really is only perhaps necessary if you're doing something like the 2D or 3D tracking. We use a third-party software by Image Systems, which requires a lens calibration as well as a fiducial marker calibration, depending on whether you're doing 2D or 3D. So those software packages do have lens calibrations in there, assuming it's a fixed focal length of lens. If you're doing 3D, what you do is you place fiducial markers down the center line, the center line of the flight path, and when you trigger like a dummy run, if you like, a static run, the mirror moves, you capture images of the fiducial markers downrange. The tracker can then output those images and also the mirror position as well for every image. Typically, these aren't time stamped, generally speaking. They're all taken from a common trigger, which comes in from the muzzle flash or whatever. So the software can take all this information in, and that's how it tends to be calibrated. So from that, you can get velocities, yaw and pitch of the projectile as well. I hope that answers the question.
Yeah, I think so too, Jolyon. Thank you very much. Unfortunately, I think we've reached our time limit here. So I see there's a few remaining questions. So again, don't worry, these will be answered offline. So again, I'd like to thank both Jolyon and Stéphane for participating in this joint webinar. Thank you for your time. Thank you for everyone to participate.
Thank you.
Okay.
Thank you for being
Thank you,
here.
everyone. Have a good day. Cheers.
Thank you.
Yeah. And see you next time on our next webinar. Thank you very much.